I identify rational and irrational numbers? Well, I'm going to try to keep this video around 10 minutes, give or take a couple. So it might be closer to 15, might be closer to 7, but I generally take about two days to kind of get people's feet wet in understanding this process. But basically, you've got these two different categories, and we just want to know, like a number like 2, is it rational or irrational? Or how about this fraction? How about 1/4? -100? Square root of 9, 7/10, how about 0.1 repeating, pi, or square root of 12? Any of these numbers, you should be able to look at them and go, it's rational or it's irrational. And this is something that's now taught in 8th grade, and it's just kind of nice because it keeps the numbers kind of packed away in your mind, and it lets you see how they're different. And then when we start talking about imaginary numbers and other things like that, it lets you further build upon your understanding of the numbers in math world, so to speak. And we see these numbers all over the place. Um, well, let's think about how rational numbers and irrational numbers are bound together. There are two different offshoots of what's called all real numbers. One side is rational, so I'm going to be building kind of like a little bubble map here, and the other side is irrational. And the first thing that we're going to look at would be rational numbers. What do we know about these rational numbers? Well, if you take a look at any fraction, like let's see, 1/4, it's a fraction. The bottom number's not 0. Hey, that's rational. Let's take a look at another fraction. Remember that one I popped up here, -200 over 613? That bottom number is not 0. The bottom number can't be 0, but it is a fraction. So -200 over 613 is considered rational. But it's more than just fractions. It's so much more than just fractions. It's also, see here in red, any number I can turn into a fraction. So when we looked at the number 2, that is a whole number. It's also an integer. It's positive. And so you can turn any of these integers into a fraction by just putting a 1 underneath it. So can I turn 2 into a fraction? Yes. And that answers this question of, can I turn it into a fraction? Yes. So 2 is considered a rational number. Also, not to leave the negatives out, I threw up there a -100 earlier in the video. Yeah, that also becomes a fraction, so -100 is also considered a rational number. So any number that is a fraction, with the bottom number not 0, or any number that I can turn into a fraction with the bottom number not 0, I can make it a rational number. And those are pretty simple. What about a square root of 9? Well, at this point, you should be familiar with square roots. If not, go back and review. But the square root of 9 would be +3 or -3. I could times 3 by itself and get +9. I could times -3 by -3 and still get +9. Can I turn these two numbers into fractions? Yes. So all of the answers for the square root of 9 can be turned into a fraction. So the square root of 9 I would consider rational for that very reason. Then we run into this situation. What about if I see a decimal, like 0.7? Well, I know in 7th grade, I've taken time to teach that when you see a terminating decimal, that's a decimal that just stops, you look at the last place value of the decimal. In this case, it's the tenths, and that means I put a 10 underneath it and a 7 on top. So 0.7 or 7/10 becomes a fraction of 7/10. When I look at this situation, 251, the last place value is this 1, and that's the thousandths place. So I put 1,000 for my denominator, and I put 251 on top. Sometimes you can simplify the fraction, sometimes you can't, but it didn't ask if you simplified it. It just said, can you take a number and turn it into a fraction? So any type of terminating decimal, basically a non-repeating decimal, we can turn into a fraction. But now that I've mentioned repeating decimals, let's take a look at 0.1 repeating. And you know it because you see it on your calculator when you see it like this. Can I turn 0.1 repeating into a fraction? If I used my old method of looking at the last place value, well, that's a 10th place, so I put a 1 over it. And if I check it in my calculator, 1 divided by 10 it just equals 0.1. It doesn't go on forever. So that strategy does not work for us with repeating decimals. Repeating decimals are kind of like in two categories. You've got the type where, let's just say it's 0.213 and the 213 repeats, meaning it's like this, 213, 213, 213, and it keeps going in that pattern. Then we've also got another situation where it's like this, one with just the 6 repeating, not everything after the decimal, but just like a certain portion of the decimal. Now, this one down here is a little bit of a different situation. We're going to focus on these top two first. If everything under that repeating bar covers everything after that decimal, and you see we've got one number after the decimal and it's underneath there, you just ask yourself, well, how many decimal places are underneath that repeating bar? One. So put 1 9 for your bottom denominator and just put that 1 on top. 1 divided by 9 equals 0.11111. So that works. How many decimal places do we have under this repeating bar? 3. 1, 2, 3. And every single decimal place after this decimal is under the repeating bar? Yes. So we're going to put 3 9s on the bottom, and 213 goes on top. And when you divide 213, this top number, by the bottom number, you'll get 2.13 repeating. You'll see this on your computer screen until it runs out of places and has to round up. And that trick does not work for this because the repeating bar doesn't cover over everything right here. I don't want to get into it. Usually it would take at least 2 days to get people somewhat comfortable with it. But I can turn this into a fraction, so any repeating decimal is rational. Now, in case you're wondering a little bit about this trick right here, a lot of times what I would do in more mathematical approaches, I would teach them to find the place value and then subtract 1. If this is the 10th place, subtract 1 and it's 9. 10 minus 1 is 9. This is the 1000th place, so 1000 minus 1 is 999. And in the same place, 5200ths repeating, this would be the 100th place, so I'd subtract 1 and that'd be a 99 on there. We'd put 52 on top. But you can also just do this. Hey, they're all covered by the repeating bar. It's 2 numbers there, so just put 2 9s there. It's all covered by the repeating bar, so put 1 9 there. 3 place values all underneath the repeating bar, put 3 9s there. It just does not work for this type of situation for that little trick to come about. Now, that's almost 8 minutes, and it's taken us that long to just cover rational numbers. Have no fear. At this point, we're going to take a look at irrational numbers. So irrational numbers would be anytime you see pi, okay? If you see pi in there, it has a way of changing a nice rational number. Pi is a number that goes on forever, and there's no pattern. So it doesn't stop like 0.7, it goes on forever. It has no pattern like this repeating decimal. This has a pattern of 1 repeating, or whatever the repeating pattern is being shown there. So there's no pattern and it does not stop. So these go on forever and there's no pattern. Also, you would run into this when you see imperfect square roots, because like the square root of 2 would be something like, I think it's 1.4, but then it just, you see a whole bunch of decimal places. It goes on forever. It's not repeating. It's not terminating. Well, it's irrational. These are the two big types that you will see for irrational numbers. Very rarely do they show you a decimal version that goes on forever without repeating. So if you can identify the imperfect square roots in pi, you'll get probably 90 to 95% of these problems identified correctly. Now, pi and imperfect square roots, they have a way of messing up nice little rational numbers. Like if I took a rational number of 2, see this 2, and I can turn it into a fraction, so it's rational, and I multiplied it by pi. Well, pi was like 3.14, you know, it just never ends. And let's multiply it by 2. Well, it's going to have to multiply all of those decimals, and then once it gets here, it's still going to have to multiply this, but it's going to be 6.28, and then it just goes on forever, and it's not going to be a repeating decimal. It's not going to be a terminating decimal. It's going to be a decimal that goes on forever with no pattern. So it has a way of mutating that nice little number into in irrational numbers. So here's my rule of thumb. If you see a pi sign involved, it's irrational. If you see an imperfect square root involved somewhere, it might have other rational numbers around it. It's irrational. That's the two biggies. And then the rational numbers, if you just see these numbers here, you see numbers that you can turn all of them into um, fractions, you're good to go. But if you see these involved at all, it changes everything and automatically makes it into an irrational number. So let's get a little bit of practice. You can see that both pi and the imperfect square roots are decimals, and they never end and they don't repeat, and that's what makes it different from these. But the big test we do is can we turn it into a fraction? And we can turn all of these into fractions. These two, because they go on forever, sorry, we don't know where the number ends, so we can't really get a hold of a way to represent it as a fraction. Now, here's 12 questions. Pause the video, take some time, take a guess, look at each one of these, and see if it's rational or irrational. Make a little notation so we can see what you think it is, and then hit play in just a second after you're ready, okay? All right, so at this point, we're going to go ahead and check it. Number 1 is 7/10, I can make that into a fraction. That would be 7/10. 0, can I make 0 into a fraction? Yes, 0/1, okay? Um, I said the bottom number can't be 0. I didn't say anything about the top, so I threw that one in on purpose. What about negative 5,389? I can make that into a fraction. I just put a 1 under it, okay? What about this one, the square root of 64? Well, 8 becomes a fraction. Negative 8, the other answer, can become a fraction. So that's good to know. What about the square root of 15? Why do I know it's irrational? It's not a perfect square root. It's imperfect. Perfect square root would be square root of 16. The one below it is square root of 9. So this is stuck in the middle. It's imperfect square root. The cube root of 8. I did not go over this. The cube root just means, hey, what number times itself 3 times equals 8? And that's 2 times 2 times 2. So the cube root of 8 equals 2. Can I make that into a fraction? Yes, I can. So as a result, I know that is rational. Now, here's the tricky question. We said any fraction where the number's not 0 is rational. Well, it's a fraction, kind of. This is not 0, but we do have pi on top. However, this pi is going to be divided by that 4, and it's going to mutate this number after we figured out what that is as best as we could estimate it into an ongoing decimal that does not repeat. And there's not going to be a terminating decimal there, so I'm sorry, pi is involved. It is irrational. Same thing's happening here. This is an imperfect square root. It's going to be multiplied by -1. There's like an invisible 1 right there, and it's got a negative sign in front of it. However, it's still going to be divided by 4, and this is an imperfect square root, which means the decimals go on forever without repeating. It will be irrational. If you see them involved, it's irrational. See this right here? The 5 is multiplying the square root of 3. 5 is absolutely a rational number, but it's multiplying. 5 is a rational number, but the square root of 3 is an irrational number. If it's involved, it's irrational. This is a repeating decimal. You don't know how to turn this into a fraction with this style, but I wanted to test you. It is repeating, so it is rational. Number 11, I hope you understood that any fraction with the bottom number not 0 is rational. And now this one's a little trickier. It's the same thing as -1 times the square root of 2. So how many answers do we have for the square root of 2? Let's see, it could be +2, which equals -2, and we can make that into -2/1. It could also be -2 times -1, because remember the square root of 4. I just now saw that horrible, my mind got ahead of itself there. I knew the square root of 4 is 2, so, or -2. So here's the +2 for the square root of 4, and it's going to be multiplying that -1, which equals -2/1. And then this one equals +2, which, hey, we already know we can turn that into it. It takes a little bit of practice, but if you can recognize whenever there's a pi or imperfect square root, it gives you a real advantage, and then just watch out for those decimals.